I'm William Putansu, and this is my glider video report for AE1601. The goal of the project was to create a hand-thrown glider maximized for range. This report will cover the design, build, test, and flight process for my glider, Bluebell. Requirements. I laid out several requirements for this project. I took the requirements from the project assignment and modified and added to them to suit my vision of a test-based design campaign. I chose to undertake a test-based design campaign because I like working with my hands, and it allowed for real-world insight into how hand-thrown gliders function. The glider must consistently fly 20 feet in the direction of the throw. This requirement is satisfied if the glider flies over 20 feet on at least 90% of its flights. The glider should be optimized for flight distance. This is a vague requirement, but it acts as a guiding principle when making design decisions. The glider must fit in a square box 16 inches on each side. The glider must remain intact throughout the flight and landing. If damage is found, the design must be altered to prevent the damage from happening again. This is critical to a test-based design campaign. There can be no active control on the glider. The glider can only be powered by a hand throw. The glider must be primarily made from balsa wood. The glider should be easy to manufacture and test, facilitating a rapid test-based design campaign. The glider should be stable and mostly travel in the direction of the throw. This requirement was difficult to quantify, so it was evaluated subjectively. The final requirement was that the glider needed to have consistent flight results, as the glider launch would be a one-try event, so the glider needed to reliably perform well. Some requirements had clear measures of success, while others were vague, but together they provided a strong vision that drove design decisions of the glider. Hot glue pork barrel. For the initial design of my glider, I decided to build a simple cardboard prototype glider. Cardboard was chosen as the prototype's material as it was abundant and workable. The glider was intended to be as simple as possible for easy construction and modification. My three options for a wing shape were elliptical, trapezoidal, and rectangular. I first figured that the elliptical wing would be difficult to produce and even more difficult to make symmetrical on both sides of the glider, which went against my requirement of manufacturing ease. I decided on a rectangular wing over a trapezoidal wing at first, as the rectangular wing allowed for more future modification based on test results. My three options for stabilizer shape were elliptical, trapezoidal, and rectangular. I eliminated the option of elliptical stabilizers due to manufacturing difficulty. I then chose trapezoidal stabilizers over rectangular stabilizers, as small trapezoids are easy to cut from cardboard and the decreased wingtip length should result in less drag. I considered scotch tape, duct tape, and hot glue as attachment methods for my glider. I chose hot glue because it is strong and abundant in the AMS. Tape was discarded because it would complicate manufacturing compared to the ease of using hot glue. Hot glue performed incredibly well, and I chose to name both of my gliders in honor of it. I briefly considered using a dihedral wing for the glider, but as it is difficult to create, I ruled it out in favor of manufacturing ease. I placed the wing in the center of the fuselage because it is a simple design and easy to work with. The sizes for the initial glider were chosen out of manufacturing convenience while attempting a high aspect ratio, while still seeming structurally reasonable for cardboard. I also figured that the sizes could be iterated on. Ultimately, the initial design was a very basic glider. This was advantageous as it allowed for a clean slate to modify based on test results, which perfectly matched my design methodology. Manufacturing the glider was simple. While building the prototype, I chose a triangular cross-section for the fuselage as it was easy to assemble and structurally sound. A copious amount of hot glue was used, resulting in the glider's name, Hot Glue Pork Barrel. Initial flight tests revealed that the glider was very unstable. To correct this, I needed to move the center of gravity forward. I did this by adding Play-Doh into the front of the fuselage. I chose Play-Doh over hot glue as Play-Doh was easy to add and remove. Through multiple cycles of testing and rebalancing, a viable glider emerged. Now, the limiting factor on the glider's performance seemed to be lift. Therefore, I increased the span of the glider from 12 inches to 16 inches with trapezoidal wing extensions. This resulted in even better glider performance. These results satisfied the requirements I laid out. The glider consistently flew over 20 feet in a stable manner and met all the construction requirements except for consisting of balsa wood. Therefore, I proceeded to build the final glider with a design heavily rooted in that of hot glue pork barrel. Bluebell. The first step in constructing Bluebell was to sketch the glider's design. The design was very similar to that of the final iteration of hot glue pork barrel, but with larger stabilizers to improve stability. Note the error in the sketch, resulting in a 12-inch wing despite the intended span of 16 inches. For easy and rapid balancing, I designed modular 3D printed weights. They are cylinders with a square hole that the balsa fuselage can be fit through. This made balancing Bluebell as simple as moving around the weight, retaping it, and throwing the glider. I created the weight in SolidWorks to create the .stl file required to print the part. I requested 4 to be printed at the AMS. For the balsa wing and stabilizers, I used the laser cutter as it is precise and easy to use. I created this sketch in SolidWorks to export as a .dxf file used by the laser cutter in the AMS. I drew extra stabilizers in the space that would have otherwise been scrapped. 3D printing took more time than expected due to printing job mix-ups, while laser cutting was quick and efficient. While I soon realized my shorter than expected span, this was easily remedied by using the spare stabilizers as wingtips. When attaching the vertical stabilizer, I was worried that the hot glue would not have the strength to counter-torque the vertical stabilizer. Therefore, I used scrap pieces of balsa as struts to brace the vertical stabilizer. They also had the benefit of making Bluebell look cool. An additional horizontal stabilizer was added on the bottom of the fuselage for increased stability and style. Due to my modular weight design, balancing Bluebell was very easy. One weight turned out to be enough to balance the glider. I adjusted the weight to get sustained level flight. Soon I had found the optimum place for the weight. I decided to add more tape as the weight's attachment instead of gluing it, as this would allow for any future change should it be necessary. The reduced strength of the tape relative to the hot glue did not cause any problems.
2, 1.
The glider achieved flight distances of 40 to 60 feet and met all of the requirements. After some throwing practice on Tech Green, I deemed Bluebell ready to launch. Final design. The final glider design had a trapezoidal wing, a square cross-section fuselage with a modular 3D printed weight at the front, a trapezoidal horizontal stabilizer on the top and bottom of the fuselage, a trapezoidal vertical stabilizer, and scrap balsa braces to support the vertical stabilizer. All structural components were attached with hot glue, while the weight was attached with masking tape. Through finding the point where the glider is balanced when held up, the CG was calculated to be 5.5 inches from the nose of the glider. The wing had a chord of 2 inches and starts 5 inches from the glider's nose. Therefore, within the accuracy of my measurements, the CG was on the quarter chord. Through the videos of flight tests, an average velocity of the glider was calculated. Using the given equations, the calculated coefficient of lift of Bluebell was 0.32, and the calculated coefficient of drag was 0.0076. Using the modular weights allowed for excellent balancing of Bluebell in a minimal amount of time, which contributed well to its stability and consistency.
Alright, that works.
Conclusion. In total, this project resulted in a well-performing glider from a test-based design campaign. This project also gave incredible insight into the design process and associated challenges. The design could likely be improved with a longer wingspan to generate more lift, as well as a more aerodynamic weight. Were more time available, elliptical and dihedral wings could also have been pursued to minimize drag and maximize range. Additionally, airfoils could be constructed through 3D printed ribs and a thin foil covering, which may add a lot of range to the glider. Thank you.